My name's Dave Richardson. I'm at U of T, and today I'm going to present the preliminary results of a study we're doing that evaluates solar radiation and solar PV performance models using actual field data for Southern Ontario. So just a quick overview of what the presentation is going to involve, a brief introduction into the topic, and then a quick look at the modeling steps that are involved from going from solar radiation on a horizontal plane to an actual PV output and grid electricity. A look at the preliminary results of this finding of the study and the main conclusions we can draw from that, and then a discussion of the next steps for the project. So the accurate analysis and prediction of the performance of a PV module or a PV array is really important for commercial PV projects, for grid integration studies, which is my area of research, and also for policy development for doing time of use PV pricing. And so there's a number of different steps, as I'll get into, and there's many different models or algorithms that have been designed and proposed for each of these steps, but they haven't all been evaluated for Ontario, and there tends to be different performance in different regions. So a solar radiation model that works well in the Mediterranean may not work well in a landlocked climate like Southern Ontario. So it's really important to analyze these, and for a number of reasons on the slide you can see that this hasn't been done recently here. So there's two main goals for this project. One is to kind of get a best practices approach to what the modeling steps should be for the region, and second is to quantify the level of error that we can expect in that modeling process. So there's a number of different steps. I won't get into them in too much detail, but you kind of have to go through all of these things to go from your solar radiation input to the amount of grid electricity you're going to get out at the end of it. What we're focusing specifically on in this project, based on the data availability, is going from a horizontal measure of global radiation and splitting that into your diffuse and direct beam fractions, and then transferring that to irradiance on an inclined plane of any orientation. A bit of, at this point for the preliminary results, considering of the effective irradiance, so that's losses from reflection, from shading, from soiling or snow cover, and then your PV module output. We haven't yet looked at PV cell temperature models, so the results that you'll see here are using the actual measured PV cell temperature. And the results are based from the module output, so the IV curves, so that's what our power basis is, so we're not measuring the later inverter losses. So this is just a look at the models that are being tested by category. So these are the diffuse fraction models, a wide range of time periods, and the ones that we selected are based on basically prevalence in the literature that have been used in other studies quite frequently. These are the inclined plane models. The Perez model is quite a common one that's used to go from diffuse on a horizontal to diffuse on an inclined plane. And we're using both global coefficients and coefficients that were derived specifically for Albany, New York, which is rather close to our site, so to see if that makes much of a difference. And then the PV performance models, there's kind of two broad categories. One is temperature and efficiency correlations, and then the second category considers the actual physical structure of the PV module itself in different levels of complexity. So two test sites. The first is the Kortright Center, which has the solar house, as we saw in the first presentation, but it also has a solar test field. And it's part of the Toronto Region Conservation Authority, and it's located in Vaughan, just north of Toronto. And the second site is the Open Solar Outdoor Test Field, which is in Kingston, and it's jointly run by Queen's University and St. Lawrence College. So both sites are really good for this study because they have multiple PV modules of different technology types and different orientations, so we can kind of test a whole range of things. And they collect all the relevant solar radiation and ambient temperature data that you'd want. Unfortunately, at this point, we don't have a full year, which is really what you need to do your analysis, a full year of data for each of the channels, but we do have over a year for some channels. So this is why it's preliminary results at this point. So for the results, I'm going to show I'm analyzing the mean bias error and the root mean square error as a measure of the model performance. And I'm going to show the models sets working in isolation and in combination to see how that affects the performance. So for the diffuse fraction models, I've shown the 5-minute average data and the hourly average data, and this is for the Kingston site. And you can see that there's a fairly good improvement going from the 5-minute to the hourly average, which is to be expected as you're kind of smoothing out random stochastic variability. But generally, we can say that the performance of these models isn't great. 32, 33% root mean square error. It's fairly consistent with studies I've seen from other regions, so that level of error is consistent, but it isn't that good from a modeling perspective. So the main takeaway is that if you do have a chance to have an actual measurement of diffuse or direct beam radiation, then you're probably going to be starting from a better place in terms of your analysis. For the inclined plane, this is the Kingston data again, but again, only 5 months this time. The last data set was just over 2 years. The models perform much better. There's a bunch of models in the 6 or 7% root mean square error level, which is really quite good. And even the worst performing model is leaps and bounds ahead of the diffuse fraction models. So that's a promising result. You can see, though, there isn't a huge difference between the Perez coefficients for global and Albany. In fact, you could argue that the global coefficients do a bit better, which is a bit of a surprise. Now, this is looking at the two models in combination, and I don't think the color turned out as well as I was hoping. But on the right, we've got the diffuse models, on the top, the inclined plane, and this is the error that you can expect together. So there's a number of combinations that do fairly well in the 12 to 14% error range. Again, this is for the Kingston data, 5 months. But I want to point out the Bugler model here and the Skarpveit-Olseth, in terms of the diffuse fraction, in any combination they have here with the Kingston data, by far the worst performance. But when we look at the Kortright Center data, so this is an hour's worth of data, or a year's worth of data, you can see that it's changed fairly substantially. So the Bugler and the Skarpveit-Olseth tend to perform the best in combination with any other model. And overall, we can say that the performance is generally much worse using the Kortright Center data. So this is a bit of a surprise. We haven't quite figured out why there's this big difference between the two sites, but we do have a couple of possibilities. One could be a difference in tilt angle. So the data is collected on a 30-degree plane for the Kortright Center and a 57-degree angle at the Kingston site, and that may have something to do with it. There could be a seasonal bias. As we said, this is preliminary results, and we only have 5 months of data for the Kingston site, so it could be they perform much better in winter, and that may change over the spring and summer. It could have to do with the surroundings. The OSOTF, the Kingston site, is on a rooftop. It's in an urban environment, and the Kortright is out in a field, so that may have something to do with it. And our final, it could be there's a major difference in sky conditions, but this seems unlikely given the relative geographic proximity of the two sites. So this is something we're definitely going to look into and try and figure out. For the PV performance models, this is switching to Kortright Center data. And I've shown 3 different irradiance inputs to the models. The first is the broadband measured irradiance on the plane of array. The second is corrected for snow cover. My colleague Rob Andrews, who's working on this, has published on snow cover modeling. And the third is effective irradiance, so accounting for reflection losses due to the incidence angle. And you can see that there is a slight improvement as you move from left to right, which is good, but it's not hugely substantial. And then in terms of the actual model performance, it appears that the more simple models, so the PV Watts and the ideal diode in particular, and the early Ravindra model actually outperform the more complicated equivalent circuit models that include things like series resistance and shunt resistance and even a second diode. So that's a bit of a surprise. I was expecting these models would perform better. But we haven't tested them for the Kingston site. So going from the whole spectrum of the process, so going from GHI to PV model performance, it would be too much to show you all of them. It's something like 1,000 combinations. These are the best 5 using the Kortright Center data. No surprise based on the results I've already shown you that the SCART-Beat OSOTF make up the best 5 combinations for the diffuse fraction. And you can kind of take your pick with the inclined surface models. And then the PV performance models, it's the ideal diode and the PV watts that tend to do the best. Overall, the modeling performance isn't great. It's not terrible, but 22 or 23% is somewhat lower than you'd be hoping to get really accurate results. So what we can take away from this is that the diffuse fraction models really are the least accurate. So if you can get around having to use those, you're going to be in a better spot in terms of your modeling efforts. And there's a significant difference between the solar radiation models, at least between the 2 sites. So this is something that we need to examine in greater depth and figure out. It appears the relatively simple PV performance models perform much better than the more complicated ones. And that may not be based on the physical things, but you have to derive the parameters of those models in different ways. So it may be that the derivation of those parameters is flawed as opposed to the construct of the model itself. And finally, the overall performance of the models in conjunction is reasonable. It's not great. We'd like to see a bit better performance. So for the next steps, we're going to get our full year of data probably sometime this fall. We'll have it, and then we can really compare between the 2 sites, figure out why there's a difference, and get our results put together. We'd like to assess PV cell temperature models. So the PV performance models that we showed here were based on the actual temperature of the modules themselves. We don't want to have to rely on that in terms of the modeling effort, so we'll test PV cell temperature models, and then a deeper analysis of other irradiance losses. So the effective irradiance, spectral mismatch, and snow cover in greater depth. And then finally, something that would be interesting to do is evaluate software packages. So there's a number of commercially available software packages that are used often to inform decisions for PV projects. Many of these are black boxes or use somewhat outdated models. So I'd like to test the performance of these and compare them to the best practices that we can get from this study. So again, we should be done in the fall and ready to present a full set of results at that point. So I'm happy to take any questions or comments you may have.